Hello, in this session we are going to look at functions and relations. I'll start by talking about relations and then explain how this leads on to the idea of a function. Now, we all know what a relation is. It can be a member of the family, it can be your brothers or sisters, it can be your cousins, aunts, uncles, and so on. But that is relations between people, and people have relations for many reasons. The most direct is when they are all part of a family, they are born to the same parents or grandparents or great-grandparents, for example. But it doesn't have to be like that. A relation can be between two people who like each other, so they can be friends. So that's a kind of relation. Now, in mathematics, we are more interested in relations between numbers. So, when we talk about relations between numbers, we will not be talking about the same kind of family relations or even numbers being friends with each other. But in a sense, it could also be related. Right? Basically, when we talk about relations between the numbers, very often it might look as if we are just making up a relation. We're just saying that we want a number 1 to be related to the number 2. So there is a relation because we say so. And you'll find that a lot of the time it seems that way. Now, but just to motivate this idea, to not to give you the idea that a relation in mathematics is a completely random association between two different numbers, let's look at some examples that are more meaningful. Let's look at something that we have learned in algebra. Let's look at an equation. Let's look at that equation, y is equal to 2x. Now that is not really any more meaningful than putting two ordinary numbers together. But if you look at this equation, it sort of gives us a reason to think of how, say, the number represented by x might be related to y. Right? We have learned about graphs and we have calculated values of x and y. So let's have a look at that. Suppose that I list a few possible values of x, like 0, 1, and 2. Just the 3 possible values of x. I can use this equation to calculate a value of y for each x. So since y is always equal to twice of x, it's quite easy. I just take each value of x and multiply it by 2. So 0 times 2 is 0, 1 times 2 is 2, and 2 times 2 is 4. So we can now say that 0 is related to 0, 1 is related to 2, and 2 is related to 4. And the reason why I can say that is because I got them from this equation. Now, you might wonder, what if I use a different equation? Why do I have to use this equation? And you're quite right, I don't. I can simply make up another equation like y equals to x squared, or y equals to x plus 2 instead of x times 2, and I can have another set of possible values of x and y. But that would be another relation. So in a sense, it might look a bit arbitrary, I'm just making this up, but if you think about it, it's not really so different as relations between people. If you don't know the people, you might find that some people make friends with people that you wouldn't make friends with, and you wouldn't understand that. But all sorts of relations can happen. Alright, so in this case, we are just going to be happy that it is fine, perfectly fine in mathematics, that we can just make up relations in any way we like. So using equations like that is just one possible way of making relations between the numbers. We can think of other ways as well, but for now, this will be the main thing that we look at. Now, but let's make it a little bit more general. I'm going to say that for a relation, I don't really need to use equations to make relations. I can simply take any two sets of numbers, alright, and insist that each number is related to each number in one of these sets of values for x is related to some number in the other sets which I decide just because I like to. So if I can just make up any numbers, any set of numbers here and any set of numbers here, and decide a relation between each pair of them. So that's the idea of a relation. We can just make them up as we like. But of course, if we do that all the time, it can become totally meaningless and useless. But as this session progresses, we'll try to put in some meanings and make it more useful, mainly by looking at different types of equations, and that will help us understand more about how equations can be used. Right, so to start, let's define some symbols and notations as always. If you look at this set of numbers and that set of numbers, it is basically something that I've just picked out of the blue, if you like. Now I can think of this as one group of numbers which I want to use, and another as another set of numbers, and I want to form a relation between them, and I just want to I will just decide that 0 is related to 0, 1 is related to 2, and 2 is related to 4. So I have a relation. Now, once I have done this, okay, I can do this without using the equation at all, right? I can just make this up, just these numbers, and I would give this set of values of x a name. This is called a domain. Right, it's not really given by me, but it's how it is named in mathematics. The first set of numbers is called a domain, and the second set of numbers is called a range. So there is, in the mathematics of relation, some idea about ordering, alright? Although we are looking at two numbers related to each other, we do order them into the first number and the second number. So there is an ordering there, and the set of all the first numbers is called the domain, and the set of all of the second numbers is called the range. Alright, and if you like this line joining them, this knowledge of which number is related to which number is the relation. Right. Okay, so we have learned about sets in an earlier session. We can think of this group of numbers in the domain as a set. So the domain is a set of elements. So each number in the domain is an element of this set, right? And this set of values of y is the range, right? And because there is this idea that there is a first number, and this first number is related to the second number, there is this idea of going from the first number to the second number. Now, in mathematics, we call this idea of going from one number to the other number mapping. It sort of comes from, maybe, I'm guessing here, the idea of a map. If you look at the map of a town or a country, you are looking at a piece of paper with a picture on it, which tells you where the roads are and where the cities are and so on. You're not really looking at the actual roads or the actual city, right? It's just a picture. And on the picture you'll see this road, and you'll see that lake and that river and that town and so on. So just pictures. But there is a relation between each picture on the map and the real thing, and the actual road, the actual mountain, the actual rivers, and the actual city, which is far away from you. So in that sense, it is almost like what we have drawn here. You might think of this set here as containing pictures of cities and rivers, and that set there as the real thing in the mountains and in another country. So it contains the same kind of idea as an actual map. So that perhaps is the reason why we use the word mapping. And calling it a mapping can always be confusing if you are seeing this for the first time. Alright, because this doesn't look anything like the map that we as we know it. But once we get used to the idea that the mapping here really just refers to a relation between two sets of things, of numbers, then it would be quite straightforward. The mapping is just the relation. Now, I'm going to look a little bit more about the behavior, if you like, of relations. Behaviors that are useful when we start talking about functions in a moment. Right, suppose that I make up these two sets of numbers. That's my first set, which will be my domain. That's my second set, which will be my range. Right, I've made up the domain and the range, and I'm now going to make up the relation or the mapping. I'll show that by drawing arrows. Okay, I'll draw an arrow there, and that means that I want 0 to be related to 2. Now I'm going to draw an arrow from 0 to 3 as well. So this means that 0 is related to 2 and 0 is also related to 3. Alright, and that's allowed. There's no problem at all. It's the same with relations between people. Right? I'm related to both my parents. Okay, and both my parents are related to me. Just like that. So father, mother and child. Okay, right, let's move on. Okay. Now I'm going to draw an arrow from 1 to 3. So there will be a relation between 1 and 3. Now I'm going to draw an arrow from 2 to 3. So we have a situation here where two numbers in the domain are both related to the same number in the range. Okay. I'm going to draw an arrow from 3 to 4, 5 and 6. So in this case, one number in the domain can be related to 3 numbers in the range. So the idea that I want to introduce here is the possibility in the relation between a domain and the range is the possibility that a number can be related to more than one numbers, and that we can also have more than one numbers mapping onto the same number. So both of these are allowed in a relation in mathematics. Right, so I'm now going to move on to functions. Now functions is a type of relation. It's a special type of relation with some restrictions. The restriction in functions is that if we look at this example here, is that for a function, a number in the domain cannot be related to more than one numbers in the range. So in a function, for example, this is not allowed. This relation between of 3 to all of 4, 5 and 6, this is not allowed in a function. Between 1 and 2, the relation, relation from 0 to both 2 and 3, that's not allowed either. So 0 can only be related to, say, 2 and not both 2 and 3. Okay? But it is okay for more than one number in the domain to be related to the same number in the range. So if both 1 and 2 are related to 3, that's fine. Alright, so a function is a relation in which each element in the domain can only be related to one element in the range. Right? So each element in the domain can only be related to one element in the range. But we can have more than one element in the domain related to the same elements in the range. That's fine. So this is a very subtle point about functions. Now, I'm just going to write this out so that it would be quite clear. A function is a relation in which a number in the domain. Right, I'm going to make it more general by calling it an element instead of a number. Just in case you want to think about relations between apples and oranges as well. So in which an element in the domain is related to, now I'm going to say not more than one element in the range. Right. I hope that's clear enough. So from this point on, I'm going to focus more on equations, which is often what we'll see in mathematics when we talk about relations and functions. So let me look at some examples of equations which can be functions and equations which are not functions. Right, let's look at this equation. Y is equal to x squared. Now we have seen some examples of this in the earlier sessions on graphs, and we know how to plot this on a graph. So I'm going to skip the plotting step and I'm just going to sketch the graph directly. The graph looks like this. It's a curve. Right. And now let me make this clearer. Alright, that's the y-axis, and the equation is y equals to x squared. Right, x-axis, y-axis. So what these axes represent are the domain. The x-axis is the domain, and the y-axis is the range. So we can Now, if we just look at this equation y equals to x squared and just look at the graph, we might imagine that x can be any values, any possible values, small, big, fractions, decimals, whole numbers, anything you can imagine. But when we talk about functions and relations, as I've explained just now, we are free to define, to decide what values we like to have in the domain and in the range. So in this case, I can decide that, right, x can have values, the values that are integers from -3 to 3, right? So x can take integer values of -3, -2, -1, 0, and so on until 3. So that is my domain. Okay, and the corresponding values of y we can just read off from this graph. So 3 would be here. So the corresponding value on the domain would be 3 squared, which is 9. Okay, and at -2 would be 4, at 1 would be 1, and so on. We can put points on the curve corresponding to the relation. Right. So I have this equation, and we now need to decide, to determine, right, whether this relation, okay, between these numbers on the x-axis and those numbers on the y-axis, whether this relation is a function. So this is the criterion for a function. Each number in the domain, each of this number cannot be mapped to, cannot be related to more than one number on the y-axis. So let's take a look. -3, to obtain the y value, we move up vertically until we hit the curve, and then we go horizontally to the y-axis to read off the value. And clearly, there's only one way to do that. And if you try it out for all the other points, you will find the same. Alright, if you go from 2 up to the curve, and then left to the y-axis, you can only do it one way and get one value of y. So clearly, in this example, each value of x will not have more than one value of y related to it. So therefore, this is a function. Right? We'll look at another example next. This example is y squared equals to x. Now let's look at what the graph is like. This is slightly more tricky to imagine, but we can borrow some idea from this previous example. In this previous example, we have y equals to x squared. Now in this example, we have y squared equals to x. So it's as if the rows of the y and the x are reversed. Alright, it's as if the y-axis is now the x-axis, and the x-axis is the y-axis. So the easiest way to actually sketch the graph without doing any calculation is to imagine taking the y and the x-axis from this graph and exchanging them. Alright? If you take the x and y and you exchange them, it's like taking a piece of graph paper and flipping it this way. Now if you do that, this curve will also be flipped around. And if you can try it out on a piece of paper, just do a sketch and flip it around. You need to flip it this way. Alright? You'll find that the graph would now look like this. Okay, this is flipped into here. Now if it looks confusing, think about the y-axis. The y in this graph is sort of a middle line, alright, in between the curve or the line of symmetry. Now when the y comes here and becomes x, this x should now be the middle line or the line of symmetry for the curve. And it is indeed the line of symmetry because the curve is now kind of wrapped around the x-axis. Right, so that's quite reasonable. So let's now try and decide whether this equation or relation between x and y, whether it is still a function. Right, now let's look at the possible values of x and y that we have used. So if we start from this value of 1 for x, which I simply carried over from the previous example, 1, 4 and 9. Now 1, when x is 1, the corresponding values of y can be, we can go up vertically to there, horizontally to here, it can be 1, or we can go down vertically left and to -1. So when x is 1, there are two possible values of y. It can be 1 or -1. Okay? The reason is that the equation is y squared is equal to x. When you take the square of 1, the answer is 1. When you take the square of -1, -1 times -1 is also 1 because the minus and minus cancel when you square it. So we now see that the value 1 in the domain is related or is mapped onto two possible values of y. So 1 is mapped to 1 and -1. If you look at the meaning of a function, you see that this is not allowed, because for a function, the value in the domain cannot be related to more than one value in the range. So clearly, y squared is equal to x is not a function. Right, I'm now going to explain a bit more about notations. I have written down equations relating x and y, equations like that. For example, and explained how it is a relation. Now from now on we are going to talk more about functions. So this can represent a function, a mapping from a value of x to a value of y. Now, but there are other common ways to write the function instead of an equation like that. Other ways that could also be useful that we need to learn. Now, because we are essentially having a value of x and then finding a value of y that is equal to 2x plus 1. Now let me just sketch a picture here to make this more obvious. So this is x and this is y. So just as an example, if I take the values 0, 1 and 2 as the domain, then the corresponding values of y we can calculate by substituting into the x. So that would be 1, 3 and 5. That's the relation, in this case a function. Now, each value of x is mapped onto a particular value of y, which is given by the equation 2x plus 1. So instead of just drawing, instead of drawing arrows for each and every possible number in a picture like that, we often draw an arrow directly from the symbol x to the symbol y. Okay, and quite often we would leave out the y and just write x arrow 2x plus 1. And you will see this fairly often in exam questions at high school or O level. So if you see this arrow, x arrow followed by an equation, that is a function. Right, I should be careful here. When you see this arrow here, that is a relation or a mapping. Now from now on I'm just going to use the word mapping because it's also quite often used in exam. So this is a mapping. Right, now it may or may not be a function, but I'll still be using the word function from now on. Sometimes we have to actually check whether it satisfies the criterion for a function. But let me just call this a mapping for now. So for this mapping, okay, it tells us that if you have a particular value of x, you can use this symbol, this notation, to calculate the value that x will be mapped onto. So this is just, if you like, a rather more abstract way of writing the same equation. Right? Mathematicians comes out with all these symbols. Okay. And the next thing we need to do is that, as you have seen, I can simply make up any kind of mappings I like just by using different equations or making them up. Now, it is often useful to give a name to the relation. So if I have different equations, I can give each one a name. And in mathematics, we often represent the name by a letter. So, for example, I can name this relation by the letter F. Okay, and the way I would include this in this notation is by writing f next to this thing and putting a colon in between. So if you see a letter with a colon followed by x and an arrow and then an expression here, it simply means that we are looking at a mapping, and the name of this mapping is f, right? And the mapping is from a value of x to a value that you can calculate using this expression. Another common way to write this information is like this. I would write f, which is the name of this mapping, with a bracket and with the x inside, and this would be written as equal to 2x plus 1, the expression. So basically another way of writing the same thing. So both this and this mean exactly the same thing. Now, this way of writing it is convenient when we need to do calculations, when we need to actually calculate values of y, and it makes it easier to write things down and easier to see what you're doing. So, for example, we might write this equation as y is equal to fx. Right, so this equation here, y equals to fx, means the same thing as the equation that I started off with. So that's that. I can also do things like, suppose that I want to calculate a value of y, or of this function. I can call this a function of x if I know that it's a function, and in this case it's actually quite clearly a function because this expression gives a definite answer, meaning it gives just one answer. So which means that if I have a value of x, I can use this to calculate only one value, and that's what a function must be. It must be mapped onto just one value and not more than one value. Okay, so this is actually a function in this case, and if let's say I want to calculate what the value is, what the value of this function is, when x is equal to 1. Well, we know how to do that. We just have to substitute the value of x equals to 1 into this expression and calculate it. Now, what is useful about this notation is that right, let me just say this first. So if I want to calculate x is equal to 1 and I want to explain this, I would say that if x is equal to 1, then y is equal to, so I would substitute this into there, and I would get 2 times 1 plus 1. Okay, 2 times 1 plus 1. Right, so I would say that. But with this notation, I can actually write f bracket x, but with the x replaced by 1 directly. So it looks something like f bracket 1 Okay, and this is equal to 2 times 1 plus 1. Now this gives exactly the same information as the sentence above, which is longer. So this notation f bracket x, because we can use it this way, it actually makes the notation shorter. Alright? If you're looking at this for the first time, it might not necessarily be simpler because it could just look confusing. But certainly you can see that writing it this way is shorter than writing it this way. Right? But of course you do need to remember the meaning of the notation and how to write this properly. Alright, if you write down f bracket 1, you can now calculate the answer, which is 3. Now next, I'm going to look at inverse function. Alright, that's inverse function. Now I've been looking at this function just now. Let me just write f on top of it. F is the name of the function that we looked at. So that's f. Now inverse function is the function that goes the opposite way. So in this case, we have the domain with 0, 1 and 2. So 0 goes to 1, 1 goes to 3, 2 goes to 5. Now what if I swap the two and I put the range, the numbers from the range 1, 3, 5. I put this down as the domain and I put the value 0, 1, 2. I put them down as the range. So I want to look at a mapping which goes from 1 to 0, 3 to 1, 5 to 2. So clearly, this is the same thing but in the reverse. Okay? And clearly there's a connection between this function or between this mapping and this mapping. So if I continue to assume that this reverse mapping is also a function, the usual way to write this, we would call this an inverse function, and the usual way to write the notation for this is to use the same name or letter with a -1 next to it on the upper right. So it's like a power. It's as if we are writing f to the power of -1. But here is what we have to be careful. Alright, the -1 here does not mean to the power of. If you have x to the power of -1, that's actually 1 over x. That's also called the inverse of x, unfortunately. But in this case, f to the power of -1, in this case it really means the inverse function. So it means something a little bit more abstract, like mapping in the opposite direction to the original function. So the f to the power of -1 here does not mean 1 over f. Alright? It's completely different from that. And we'll see in a moment how to actually find the formula for f minus 1. Okay, so that's the inverse function. Now, let's start with this equation again. So this equation was fx equals to 2x plus 1. So that's what we saw just now. Now the problem here is, how do we find a corresponding formula for this inverse function? So if the original function is 2x plus 1, can we also find a formula for the inverse of f? Right. The way to do it is like this. In the first step, to make it easier to do the algebra, I'm going to call fx y. Let fx be y. So I'll write it as y equals 2x plus 1. And in the original function, we know that we can, for each value of x, we can use this equation to calculate the value of y, and those would be the values of y. Now the problem here in the inverse function is that the y values is as if we are given the y values first and we have to calculate the x values. So for example, if we know that the y is 1, now here we want to calculate what the value of x is, alright, in order to get that. So if you look at this equation, that means that we are given the value of y and we must find the value of x. And we know how to do that in algebra. We simply rearrange this to make x the subject. So let's do that. Now subtract both sides by 1 and then divide both sides by 2. And there we have the formula. Using this formula, if I, for example, substitute this value into the y here and calculate x, we will get that. You can try it out. So if you put 3 into the y there, 3 minus 1 over 2 is 1, which gives us that. So this is the formula that we need. So we have got the answer actually, but in order to present this answer properly, if you are doing an exam question, there is one more step we need to do, which is that although we understand that these numbers here came from the y originally, when we put these numbers in the first position and put those numbers in the second position, these numbers now become x. So it's like we should change the name of those numbers which were originally called y. We must now call them x instead. And those values which were originally x, we must now call them y. So what this means is that there is a renaming step in which the names of x and y are exchanged. So I will simply replace the x by y and the y by x. It's a renaming step. And then I would write x minus 1 over 2 as my inverse function. So how would I write that down? So the original function fx is written this way. The inverse function would be written as f minus 1 bracket x. Right? So instead of fx, I have f minus 1 x. So treat the whole of the f minus 1 as a name of this new inverse function. And the formula is now x minus 1 over 2. Right? So that's the inverse function, x minus 1 over 2. And we can also write it in the other form, which looks like this: f minus 1 for colon, and then followed by x, and then the arrow, and then the expression. So that's the other way to write it. Alright, the last thing in this session is to look at composite functions. Now, a composite function is what you get when you combine two functions. You can think of it as a function of a function. So, I'll use a very simple example. Imagine that we have two functions. One is fx, which is equal to 2x, and the other is gx, which is equal to x plus 1. So we'll sketch some pictures just to become more familiar with what they do. So suppose I start with the values 0, 1, 2. So my starting domain. So those values, if I apply the mapping called f, the function called f, each of these will be multiplied by 2. So I get 0 to 4. And I do this mapping. And then when I apply the mapping G, I need to add each value by 1. So each of these values will now be added 1, 1, 3, 5. So that's the G function. So that's what we mean by composite function. If I want to make up a composite function, I can make up a composite function by starting with given values of x. First, I apply the function f to calculate the answers, and then I apply the function g to those answers from f and calculate the final value. And the way we would write this is that if I think of the values here as x, okay, I can imagine starting from values of x, and then when I apply the function f, this is what I would do. fx, and I can calculate an answer for that from that. And then when I apply the function g to the answer of that, I can imagine writing it this way. So that would be g of f of x. So just as an example, to see what this means, let's say when x is equal to 1, for example, we know that if we apply this, we will get f of 1 is equal to 2 times 1, which is 2. Right, 2 times 1. I would then apply g to that answer, so g of 2 would be x plus 1, so it will be 2 plus 1, which is 3. Now if I write it that way, it would look like this: g bracket f bracket 1. Okay, so f bracket 1 we know is 2 times 1, and this gives g bracket 2, g of 2, and we know that g of 2 is equal to 2 plus 1, which finally gives us 3. Okay, so that's the reason behind this notation. This will be g of f of the value of x. So that's what that looks like. Now another way of writing that would be to leave out the outer brackets and call it gf bracket x. So which means that we give our composite function the name of gf just by putting g and f together. Now we have to be a bit careful when we look at this notation gf. The ordering is important. For example, if you say fg, it could be quite different. We'll see in a moment. So if you say gf, it means that we must carry out the f function first, like this. That's the first step. Okay, so we must carry out the function which is closer to the x, to the bracket x. We must not carry out the function that comes first when we read it from left to right. Okay, so you have to always carry out the function closest to the x in the symbol. So that's g of f of x. Right, now what I've done here is I have calculated a value for the function of f first, and then a value for the function of g. I've done it one step after the other separately. Now can we find a formula for gf of x so that we can just do the calculation in one step, or at least more directly? Well, we can. We have the formulae for fx and gx here. So let's try and find a formula for gfx. So g, I'll write here as g bracket f bracket x. Finding the formula is quite straightforward. We would follow similar steps to when we do the calculation. So I would substitute f of x, I would substitute the formula 2x into this expression. So that would be g of 2x. Okay. Now we then look at the formula for gx equal to x plus 1. So x is now 2x, so I would substitute 2x into the x here. That gives 2x plus 1. And that's the formula for gf of x. That would be 2x plus 1. And I can actually use this to do this calculation. So for example, if I want to find gf bracket 1, alright, which is the same as that, instead of doing it in 2 steps like this, I can use this formula directly and say that this is equal to, substitute 1 into the x there, 2 times 1 plus 1, which is 3. The same, 3 there and 3 there. Okay, so right, I hope you can see that number there. So that's the formula for gf of x. Now I did say just now that the ordering is important. So for example, gf of x might not be the same as fg of x. Now I have found the formula for gf of x. So let's now try to find the formula for the reverse, for fg of x, and see what it looks like. Right, fg of x. So that would be the same as f bracket g bracket x. Okay. Gx is x plus 1. So let's substitute the expression x plus 1 into here. Gx is x plus 1 from there. So now we have the function f of x plus 1. Now f itself is 2x, so I should substitute all of x plus 1 into the x there. Now we have to be careful when we do that. Now this is 2x. We must not simply replace the x by x plus 1, and then it looks like that. The 2 is multiplied by this number, and that number is x plus 1. Meaning that you really need, if you actually know the value of x, you must really calculate x plus 1 first before you multiply by the 2. And we represent that by putting brackets around it. So that is very important. And you can see that if you put brackets around it, it's completely different from not having brackets. So 2x plus 1 is now the formula that we have found. Okay, I'm just going to now remove the brackets to give 2x plus 2. So fg of x is 2x plus 2. Now if we have it the other way around, if we have gf of x, that's what this was, gf of x, the answer, the expression we have seen is 2x plus 1. So that's 2x plus 1, and this is 2x plus 2. Clearly, fg and gf are different. So that proves the point. Of course, it really depends on what the functions are. It doesn't always have to be different. It just means that in general, they may not be the same. We can think of a very simple case in which fg and gf are the same. It is when the two expressions of the functions are exactly the same. So in which case f and g are the same as each other. So fg and gf are just the same thing. Okay, we'll stop here for this session. See you next time.